Switch names.
Okay, here we go. Taylor, I'll erase your name. It's probably stressing you out there.
Yeah.
It's okay. All right. Now, everybody look at calcium's electron configuration on the old reference paper.
Wait, you two share. Well,
I just need one person. Just tell me what it is.
2-8.
oh, I shouldn't look at it.
All right. Again, it completely kills me that that's how the Regents has it, because it makes absolutely no dang sense. All right. Now, write that down. We're just going to start getting into practice props here. How to write electron configurations. I'm going fairly slow because this is the only time I teach how to do it. From now on, you need to know how to do it. Okay. Now, use the order of fill and write the correct configuration. I'll do it with you. The way we do this, these two electrons are in the 1s orbital. I'm going to do this one really slow so we understand how to use that order of fill and how to start writing the correct electron configurations. After 1s, what comes next? 2s. So the 2s, and what's after 2s? 2p, that's where 8 and I'm going to kind of do this to separate them. All right. Then I'll rewrite it like how you're supposed to on a test for it. Okay. Now, what comes after 2p?
3s.
3s. And then what? 3p. That's where those 8 electrons go. And now, what's after 3p? 4s. And that's where those two are. So when you write or look on the reference table in Regents, it's 2882. The kids who really try and figure things out get all confused because they say, wait a second, you're telling me first level holds 2, second level holds 8, third level holds 18, and the 4th, 5th, 6th, 7th, they all hold 32. And that is something you guys need to know. That's how many. So the 4th, 5th, 6th, 7th, they all hold 32 electrons if they're full. So this is what trips kids up. And I tell them, okay, you have to fill from your first level, just what I just went through with you guys. You got to fill your first level, then second, then third. So you can't move on until you fill the level below it. This is confusing. This should be a 10. It should be 2, 8, 10 according to the rule here. But it's really hard in Regents to explain what the heck's going on here, so I just tell them that's how it is. That's it. I don't get into this because it's really hard to explain why that 2 is there. And I might have said the same thing to you guys. But now, hopefully you're starting to maybe get a little bit of the understanding. This 4s is more stable than the 3d. So in real life, the electrons will not go into the 3d. They'll go into the 4s first. Once the 4s is filled, then it goes into the 3d, and that would come over here. What's the first element that uses the 3d orbital? I didn't pick calcium just randomly. I did this on purpose.
You group in carbon.
So calcium, stay with me, look up here. Calcium is 2882, and we're going to stop saying that pretty soon. But calcium uses all of these. So the 4s is filled. S can only hold 2, there's the 2. What's the next element? Scandium, number 21, is the first element up there that uses a d orbital. Because if it had one more electron, okay, one more electron, look at SC, what is the electron configuration? 2892. So now it would go into the 3D. So now the 3D would be here. So if this was scandium, all right, this is where it gets confusing. All right, this is SC. So 8 would go here, and then one of those would go there.
Oh.
Because this holds 8. 2 and 6 is 8, and then this would have that one extra would go into 3D because your 4s is filled now. So the reason I show you the order of fill is so you can get the proper order when you're writing these electron configurations. But let's go back to the beginning of class. Look over here. This is called the S block. calcium has its valence electrons, and now here you go, right? This is going to make you happy. In the 4s orbital. Magnesium has them in the 3s. Beryllium has it in the 2s. Lithium is 2s. Sodium is 3s. Potassium is 4s. But here's how it works. This is 2s1, 2s2, 3s1, 3s2, 4s1, 4s2, 5s1, 5s2, 6s1, 6s2, 7s1, 7s2. So depending on where they are, you know calcium has a 4s2 orbital because it's the second one on the fourth period. So that's s1, s2. Scandium is 3d1, then it's 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, 3d8, 3d9, 3d10. Gallium is, because it's in the fourth level, 4p1, 4p2, 4p3, 4p4, 5, and 6. So the P block, the D block, and the S block help you figure out, okay, how am I going to write this? Well, I know because I'm just going to count. I know this is the S block, so it's 1, 2, so that's S2, 4S2. I know this is where 3D starts. Kids get confused with that. They're like, why isn't this 4D? And that's because it's more unstable. In other words, you fill your 4S first, and then you drop back down to 3D. So again, keep your eyes over here. All of these here are 3D. These are your 4D. These are your 5D, your 6D. So it's off one because of the way you fill it up. So again, if I want to know where are my electrons for iron, I would say, okay, it's the D block, so that's D1, 2, 3, 4, 5, 6, so that's 3D6. If I said, okay, where are the electrons for chlorine? I know it's in the third level, so I count. It's 3P, because it's third level, P block, 3P1, 3P2, 3, 4, so that's 3P5. That's how, when I started the class, I wanted to get back to it to kind of show you this is confusing and kind of hard, but this really helps if you know how to read it. And obviously, it's just going to take practice. Is that making a little sense? So, here's calcium's electron configuration. See if it makes sense to you. And then I'm just going to have you practice a few of them. We'll go over them. Here we go. So calcium is 1s2. That's how we show the electrons. It's like an exponent. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. That is calcium's electron configuration. Just copy it down. The exponents are the number of electrons. The big number is the energy level, so 1 through 7. The S, P, D, whatever it is, that's your sublevel, your orbitals. And then the exponent is the number of electrons. So, this 2882 business, there's 2 here, 2 plus 6 is 8, 2 plus 6 is 8, and then 2 here is 2. So again, the big number is the electron level, shell. Little number is the number of electrons, and then the letter is the orbital or sublevel. Okay? Now, you will have to write out orbital notations. Now, I'm not going to do it for all of them, but if we take just these, just to show you what I mean, your 3s would look like this, up, down. Your 3p would look like this, up, down, up, down, up, down. And then your 4s, we'll just do it here, would be up, down. So this is something you're going to have to do on that lab on Wednesday. Once you get the electron configuration, show me exactly where every electron is. So there's 2 in this orbital, there's 2 in that orbital, 2 in that, 2 in that, that's 6 total, and then there's 2 in the S. And obviously before we get out of here, we'll get into configurations where they're not full, and you'll see how to do that. Because there's a rule about that too. Questions before we move on? You having fun, Taylor? Good answer. All right. So, why does it make sense that noble gases don't react? Full valence shell, right? Okay, remember that. All right. I'm going to give you 2 elements. See how we do. Give me the electron configuration for, I'm going to give you 3. Rubidium, sulfur, and nitrogen. Rubidium, sulfur, nitrogen. Give me the electron configuration, and don't look at the, put your reference tables away. Because you don't have those anymore. No more reference table privileges. You just got to say, okay, RB has 37 electrons, S has 16, and N has 7. Start writing out your configuration, start with 1s. Now remember, you can use that order of fill or use the blocks. But it's going to take a little practice probably to figure out the blocks. So I'm going to help you with that, obviously. I had this cool animation that kind of did this for us, but the link is shot. So that stinks. You're going to get nitrogen wrong. Well, I mean, you might get it right, but I'll explain that. Never mind. I spoke that. You guys remember dot structures, right?
Mm-hmm.
This helps explain those too. Once you really get good at this and you understand these, your life is complete. We done yet? No? No one's looking up. So. Can't do rubidium, then just do N and S. Or S and N. Okay. Cal, which one do you want to give me? Sulfur, go ahead. 1s2.
1s2, 2s2, 2p6, 3s2, 3p6.
Mm-hmm. Add up all your little numbers. That add up to 16.
Oh,
4. Very good. Now, so, but again, you guys, once you get used to this, you don't have to do math. Look over here. This is your S block. It's important to try and use this little trick. This is the fourth element. 1, 2, 3, 4. So I know it ends with a 4. My 3p4 because it's in the third level. 1, 2, 3, 4. So 3p4. The way this can help is now you just go backwards. So you know this is 3p4. You just need to remember what's before the 3p. The rest of it is full. So all of this is going to be completely full. This is where it ends on the periodic table. So you got your 1s, 2s, 2p, and 3s. They're all going to be full, and that's not full because if it was, it would be a noble gas. That would be argon. So if argon is non-reactive because the 2 and the 6, it's full. That's a full valence shell. This is not a full valence shell. All right. So again, you start with your 1s. So here's your 1s, 1s1, 1s2, 2s1, 2s2. So that's how this works. All right, and you fill it all the way up to 3p4. Good. Who wants to do rubidium? Who wants it? Kristen does?
Sure.
Go as far as you can. Here we go.
1s2.
1s2.
2s2.
2s2.
2p6.
2p6.
3s2.
3s2.
3p6.
3p6.
4s2.
4s2.
3d10.
3d10.
4p6.
Forgot my 4p. Yep.
5s1.
5s1. Right. Sorry, I ran out of room there. Right. Good. So he's right because look, rubidium is here. This is 5s1. Now we jump up here. Krypton has a full valence shell. What is that shell? It's 4p6 because it's 1, 2, 3, 4, 5, 6. So I know krypton is 4p6. Then I move on to here and it's just the next one more electron. So this is your 5s. So you don't need to memorize the order of fill if you understand how to use the blocks. So there's your 4p6, so that's got to be 5s1. You just the hard part is remembering how to fill this up. All right, and you can memorize it, or again, look up here. This is our 4p, so all of these are 3D. All of these are 3D. This is my 4s. This is my 3p, my 3s. So you can work backwards, and the more you do this, the more you'll get used to. You guys will all remember basically 1s through 4s. You'll or 3D. That gets you zinc. You'll probably just memorize that eventually. That's zinc, 3d10, and then after that, just look at your blocks. Okay? Now, you want to know the easy way to write this? Of course you do. That's acceptable on an AP test. That's called a noble gas core. What that means is you put krypton in brackets. What does that mean? It means all of this is in the brackets. You don't need to show it. You just need to write 5s1 for RB. Because RB's configuration is literally identical to KR, except for the 5s. That's called a noble gas core. It's completely acceptable. Test, lab, quiz, AP test, in college, doesn't matter. Okay, that's completely acceptable. I'm not going to let you do it right away, because I want you to get better at this, but you can do that in the future. All right? Can you do it for sulfur? Yeah, because sulfur is a neon core, right? Neon goes up to 2p6. So all of that is in here, and then 3s2, 3p4. So you can use it for that one too. So any element past helium, you can do that. I mean, even lithium. Lithium technically, and this is silly, because the time it takes to write that, takes longer than writing 1s2, but would be 2s1. That would be lithium. No one really does that. The only time this is useful is when you get up to like francium. Well, francium is just radon, in brackets, 7s1. Take you 2 seconds to write that configuration, instead of writing out, a million letters and numbers. Okay, so that is acceptable. Okay, what about nitrogen? Luke, what do you got?
1s2, 2s2, 2p3.
1s2, 2s2, 2p3. Very good. All right. Questions for me before we move on? We're going to start learning some more stuff. I'm going to give you a handful of practice ones, so I'm going to move on past just writing them out. Are you guys sort of picking up the blocks and how that helps? Okay. Now, here's what I want you guys to do. I want you to write the orbital notation for these three for just the valence electron. So I want the orbital notation for the 5th level, because that's the valence, so for your 5s. I want the orbital notation for the 3rd level, so 3s, and then 3, well, you know what, do it this way. In general, you should put them next to each other, so 3s would be here, and then 3p would be there. And then same thing here, I want the orbital notation for the valence shell, so 2s, and then 2p. So go ahead and write those down. We're gonna do the orbital notation. Now, if you are, hold on, I'm just gonna do it with you. So if you're using a pen, you'll just have to cross it off because you're gonna do nitrogen wrong if you don't follow here. All right, I always forget the name of this rule. It's called the Pauli exclusion principle. Yes. And Hund's rule, so it's a combination of both. All right, here we go. Obviously, this one's easy. 5s1, you just put one arrow, and it always goes up. If you put it going down, you'll still get credit, but the general rule is it always goes up. Okay, so that's your orbital notation for rubidium, for the valence shell. Valence shell is the last, the outermost energy level, and I do want to comment on this. This gets confusing to kids. If you look at, I'll take zinc. Okay, so zinc, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. So that's zinc's electron configuration. Where are the valence electrons? No, I got you. I tricked you. It's right here. So zinc only has 2, and that's why I did it. Nicole, you're not alone, trust me. What happens when we start writing these out, kids will think back to regents and say, oh, it's the last number. So the last number is 10, but remember, the valence is the outermost energy level. The 4th level is the outermost energy level. And the kids are like, wait. But you said it like dips down in the 3rd, so it's not really the outermost. Yes, that's the analogy, but it's really hard to take this abstract concept, right? So not technically, the bigger the number, that's further from the nucleus, so the 4th level, so that would have 2 valence electrons, okay? So I just wanted to throw that out there because that gets confusing. All right, back to this. 3s2, up, down. Here's my 3s2. 3p4. Now, each orbital can hold 2 electrons, right? Actually, yeah, you'd probably do this one wrong too. Guess what? If you guys probably did it the way you wanted to, you would do this. 1, 2, 3, 4. But that's not how it works. How do you think it works?
1.
You put 1 in each orbital first, then you start filling them up. You put 1 in each orbital first. Now, why does that make sense? Taylor, why would that be the correct configuration there?
Because there has to be electrons in an orbital for it to exist or something.
Okay, not a bad answer. Not a bad answer. Yeah, I'll take that's pretty good. She says there has to be an electron in an orbital for it to exist. Yeah, technically all these orbitals are available to all the elements at all times, but unless an electron's in it, it's not really there. That's good. There's another reason. I'm just going to give you the answer to save time. Electrons have negative charges, so if they can be in a room by themselves, they'll do it. If they have to be together, that causes repulsion, so one of them's going to have to start spinning the other way, which kind of costs energy. It takes some energy to do that. So all of these electrons and all the elements would prefer to be in their own orbital first before they have to start pairing up. That's the explanation. It's because the negative charge and the repulsive force there. So why is that really, really, really important? It's really, really important for this and actually for sulfur, and I'm going to explain in a minute. This is up, this is down. Now nitrogen looks like that. That's really important. And you already know why, you just don't realize it. What's the dot structure for sulfur look like? How many dots does sulfur have? 6. Right here. 2 plus 4, 6 valence electrons. And you guys remember when I taught this, you go 1, 2, 3, 4, 5, 6. Okay, now, back in Regents, you just do it, you memorize it, you get through it, and you're like, oh good, I know what I'm doing, I know how to do that. 6 dots, 6 electrons, good. Now it's a little bit more complicated, but I also think it's easier. Why does this make sense looking at this?
In grade 2 on its own.
Right, these two are right here. These two, which are paired up, are right here. They cannot bond. See what happens when these elements start to bond, and this is going to all start to click. These electron configurations really help you learn a lot about the class. This is what happens. Those blue arrows are from like hydrogen atoms, let's say. So hydrogen sulfide gas, H2S, when it forms 2 covalent bonds, one bond goes here, right here, and then one bond goes here. So these orbital notations and these accurate electron configurations really give you a lot of information into how they bond, why they bond, how many bonds they can make, where the pairs are. So that's a 3s, that's a 3p, this is a 3p, and that's a 3p, but they're by themselves. That's where the bonds would form. Sulfur can't bond those. Well, they can, but you don't know that yet. So we'll get to that. But anyways, if the electrons are by themselves, that's when they can bond. So it makes sense that's sulfur's dot structure. Now nitrogen's dot structure has 5 valence electrons, 1, 2, 3, 4, 5. It can make 3 bonds. 2 there, and then 1, 2, 3. If you were to do this like that, right? So not following this rule, Pauli exclusion, and Hund's rule it's called. All right, which you don't need to know. But if you did 2 and 1, this would look like that. That's not how nitrogen works. Nitrogen forms 3 bonds. So what I like about this, and hopefully you're starting to see this and it clicks, is it explains why we learn what we learn. It explains why dot structures look the way they do. It's not just because somebody made it up, it's because that's how the electrons actually exist in the orbitals and in the atom. So it's really important to remember that. 1 electron per orbital first before you start filling them up. Okay? Now, give me carbon's electron configuration. Go ahead and write that down. Carbon's electron configuration. Hopefully we're getting quicker at this here. Okay, carbon. Ben, oh, that's sulfur. That was weird. Ben, go ahead.
1s2, 2s2, 2p2.
Very good. And again, remember, you can look over here and see, look, second level, 1, 2. So 2p1, 2p2. Or, another way to check, you know there's 6 electrons, 2, 4, 6. So then the little numbers have to add up to the atomic number. Okay. Now, if we do the orbital notation, here's my 2s, up, down. Here's my 2. This is really the way to do it. I don't know why I did it the other way. When we're writing these out, you put all the second level or third, you put them all together, and you put the orbital underneath it. It's not a huge deal. As long as you label it, you're fine, but that's technically how you do it. Now, if we do it the correct way, you have 1 up, 1 up. That orbital's empty. It's available if you need it, but it's empty right now. Okay. Paige, remember carbon's dot structure? Well, it has 6 total.
Oh, right.
How many valence electrons does it have? 4. I don't know if you guys remember, but carbon makes 4 bonds. Hopefully you remember that. That's something you should know already. Okay, that's carbon's dot structure. Nicole, what's wrong with that? Right. These two, so really carbon's dot structure should look like that. But that's not how carbon actually bonds. I don't know if anyone remembers this, but I think I told you sometimes the regents will do that for aluminum, but like on a test to say which of the following is the correct dot structure for aluminum, and that'll be a choice, and it'll throw kids off because kids will say, all right, I know it's 3 because I know how to do it, and I learned it that way, but they want to do that. So that's how I teach it, but then on a regents it might have this. Same thing for carbon. On a regents, or an AP test, I mean, they're not going to give you this too easy, but they'll put two together because that's how it actually looks. But what happens is carbon takes this dot and says, I'm going to use that empty orbital because it's more stable, and it puts the dot by itself. There's a term for that we're going to get into in the next unit called hybridization, and that's how carbon bonds. I'm just kind of sprinkling that in there, a little teaser for the future. All right. So that's why we learn this. We learn the orbitals, we learn the configurations to really understand bonding. That's what it's all about. All right. Questions for me before we move on? I only have a little bit of time. Are we picking this up a little bit, I hope? Well, we'll find out. Okay. All right. There's, we got time. Two terms here I want to give you. Tomorrow we'll get into all that. Oh, and of course, there's exceptions up there that don't follow the rules that you just learned. So we'll talk about those tomorrow. Here we go. Anyone else laughing? No? Diamagnetism. I always spell that wrong. Oops. Magnetism. Okay. Ever heard of these terms before?
No.
Okay. What metal up there is pretty strongly attracted to magnets? What is it? Iron, yes. Does anyone know anything that is not really attracted or actually repelled by a magnet? You probably don't know that. This is what the lab is about, by the way. Well, I'll give you a hint here. Manganese is really attracted to a magnet, but zinc is not. What's the difference? So Mn and Zn. Here we go. Mn's configuration. If we use the noble gas core, there's argon, and then who can finish it? What after argon? What comes next? 4s2. That's K and Ca, and then 3d. Mn. Count. 1, 2, 3, 4, 5. 3d5. Okay. Zinc is argon. 4s2, 3d10. Let's do the orbital notation for the 3d. For both of these. Manganese would have one arrow in each box. Zinc would be full. This is called paramagnetic, which means attracted to magnets. This is called diamagnetic, which is repelled by magnets. What's the difference between these two? What's the difference? Right, this one has all the electrons spinning the same direction. Think of it this way. I told you one spins one way, one spins the other, positive a half, negative a half. Think of this as like there's no charge here. But here, there's a net charge because there's not another one to cancel it out. So something with that charge is going to have an effect with magnets. It's going to be attracted to magnets. We'll talk more about that tomorrow. Homework, real quick. Give me the electron configurations for potassium, bromine, iodine. I'm going to give you some ions too. Let's do Ca plus 2. Let's do Cl minus 1. And we'll do O minus 2. And I'll do one more. Let's go CO plus 2. I want the electron configurations for all those. And that's it. You're going to have more down the road, but that's it. Okay. Don't use the noble gas core. That's cheating. Write down all the levels.
So much easier.
Don't cheat you, okay? Use it. Not yet. Need anything? Let me know. I'll be after school. I don't have a meeting or anything.